The results of an experiment are called statistically significant if they are unlikely to occur by random chance. That is, if it is unlikely that the results are due to the possible imbalances created by the random assignment. For example, now we do have to my activity with the caffeine didn't work terribly well, so this would be assuming, okay, so let me go back and look at something here. Assuming my results weren't this inconclusive result, but assuming instead that we had results that look like this. So this paragraph is referring to results where people who drank caffeine did have a higher change in pulse rate than people who did not drink caffeine. So assuming that is true, then I'm going to read this paragraph here. For example, if caffeine really has no effect on pulse rates, then the average change in pulse rates of the two groups should be exactly the same. Of course, ours were actually, but they shouldn't have been. However, because the results will vary depending on which subjects are assigned to which group, the average change in the two groups will probably differ slightly with different random assignments. Thus, whenever we do an experiment and find a difference between two groups, we need to determine which of these two things is the cause for the observed difference. Number one, this difference could be attributed to the chance variation in random assignment, or two, there really is a difference in the effect of the treatments. It's considered statistically significant if the difference cannot be attributed just to chance random variation, and it really shows a difference. So how do we know if the results of the experiment are statistically significant? To do that, we are going to do this simulation here. We're going to look at another experiment and do a simulation. So here's the situation. To see if fish can help to reduce blood pressure, or fish oil, I'm sorry, can help to reduce blood pressure, 14 males with high blood pressure were recruited and randomly assigned to one of two treatments. Before starting the treatments, their blood pressure was measured. The first treatment was a 4-week diet that included fish oil. The second treatment was a 4-week diet that included regular oil. At the end of 4 weeks, each volunteer's blood pressure was measured again, and the difference in diastolic blood pressure before minus after was recorded. The results of the study are recorded below. Note that a negative value means that the subject's blood pressure increased, because we're doing before minus after. We hope to see that the before is bigger than the after. Okay, so so here are the results. The fish oil, the group, showed an average reduction in blood pressure of 6.57, mean meaning average. The regular showed an average increase really of 1.14. So the difference in mean reduction of blood pressure from the fish oil group and the regular group is, we say X bar, which is the symbol for mean or average. The average of the fish oil group minus the average of the regular group equals 7.71. So the question, is the difference in mean or average reduction of blood pressure statistically significant? In other words, assuming that fish oil made absolutely no difference in the reduction of blood pressure, how likely would it be to see a difference as large as 7.71? Now, I'm going to repeat this because this is really important. If we were to assume that fish oil actually did not make any difference in blood pressure, and that all of these differences in blood pressure were merely random variations among individuals for other reasons, how likely would it be that the fish oil group had this much bigger of a reduction than the non-fish oil group? So how often would we see these results just by random chance? So to explore that, we're going to do a simulation. And here's how this worked. I printed up cards with all of the 14 blood pressure differences for the 14 men in this experiment, or 14 individuals. I don't know if they were all men. And I cut them apart and made them into cards like this. And we shuffled the cards, and we randomly dealt 7 into each group. So we're assuming, random assignment, that these blood pressure differences aren't based on anything having to do with fish oil. They're just random variations. So we're randomly assigning them to 2 groups. Then we are going to take those two groups add up all of the values. So assume that all these red ones got assigned to this group and all these blue ones ended up in this group. We're going to add up the values, divide by 7 because there's 7 in each group, and subtract them. And so what we end up with, let me extend this up a little bit so you can see this better. So in this case, what we ended up with, negative 2.57. Then I collected these from the entire class, and they were in a list. Okay, so here are all of the different values that we got. 63 different differences, some positive, some negative. So we did this over and over again. So each member, each group in the class did this multiple times. This would shuffle the cards, divide them out, and go through this procedure. And this is what we ended up with, is these results. Right here, 7.57. Here's the 7.71. That was the observed difference in the treatment group, and then there was one that was bigger than that. So there were 63 of these altogether, and only 2 of them were 7.71 or greater, which was a percentage of about 3%. So what did we conclude from that? So I drew this on here. Here's our results. There was only a 2 out of 63, or about 3% probability of getting a difference of 7.71 or more just by random chance. So we're going to reject the explanation that it happened by random chance. That is just far too unlikely to have happened by random chance. Is it possible? Yes, barely, but very unlikely to have happened by random chance. So the only other explanation is that there is evidence that fish oil does lower blood pressure. So because it was highly unlikely for this result to have happened with random chance, that gives us evidence that the other explanation is correct, that fish oil does lower blood pressure. This value, this 3%, is actually called a p-value, and it's something that you're going to talk about more second semester, but if you've seen that ever, I think you guys saw it on the pre-test, that's what a p-value is. A p-value tells us the likelihood of getting a result just by random chance. And if that p-value is very small, then we're going to reject the explanation of random chance and say there is really evidence of an association between these variables. And in this case, since it's an experiment, evidence of cause and effect association.